Hey scholars, it's Mrs. Wegerson again, and we are working on lesson 7.5, finding the area of regular polygons. And this is one of those that has a lot of definitions, and I'll probably talk fast in some spots, so remember to stop the video, rewind, listen again, then write it down, or maybe go all the way through, come get a copy of the notes from me if you need to. But I want you to understand, this is one of those that I had someone say that you gave us a lot of homework on this. And my answer is yes, I do, because in about 2 months, you're going to need to remember it. And if I don't get you to have it ingrained now, how do I expect you, especially after spring break, to remember these formulas? So it's real important that we get these down. So the first thing we need to do is remember what a regular polygon is. So I'm just going to actually write the definition up here. What's a regular polygon? Well, regular polygons are polygons that are equilateral and equiangular. That means they're both, all the sides are the same and all those interior angles and everything are exactly the same. So everything we do today is going to be based off of, regular polygons. So everything we're going to do. Now, I'm going to tell you the take home right now. The takeaway will be hexagons. The main one you're going to have to know is regular polygons or hexagons. But we're going to use this pentagon to help illustrate and put things into location, so it'd be a little bit easier, a little bit larger to work with. And we're going to go through and we're going to talk about the different parts. So for instance, we're going to have the center of a regular polygon. The center of a regular, and I'm going to do REG for regular, right? Polygon is equidistant from all the vertices. So that means C right here is the center. It's actually the center of the circle that circumscribes the polygon. So you don't have to draw that circle in, but that's where we get that from. So it's the center of a circle. We're also going to call it the center of it. Now, all those segments you see drawn to the vertices, this is one thing I did not put down as a definition, but I want you to know, those are all called the radius. So, unlike a circle, which has an infinite number of radii, a polygon only has the same number of radii as it does vertices. So like here I have 5 vertices, so I have 5 radii, okay? And when I put 2 radii, oh, actually I'm getting ahead of myself. Let me get to the next blank. Then we also have this line segment that we can draw in from the center to the midpoint of one of the sides, which will bisect that side, and we're going to use the letter A for that, and that's called an apothem, okay? So an apothem, now some people say apothem, but I like apothem because it sounds like a possum. You know, a possum, you know, sorry. Little humor to keep me going here, okay? So with this apothem, it's the distance from the center to a side. It goes smack dab, and so we mean perpendicular distance. So how many sides you can have that many apothems. So like we have 5 radii, you should have 5 apothems. Notice too, if you put 2 consecutive radii together with the side, you make an isosceles triangle. And in fact, you will have congruent isosceles triangles. And you'll have 5 here in this case. Or if you had 8 sides, you would have 8 congruent isosceles triangle. And when you put 2 of those together, this angle right here is called the central angle. So it's a central angle of a regular polygon. Okay? Now, the thing is, all of these are central angles, even this one right here. But I want you to see what's really cool about our apothem. In fact, I'm going to use green here. And I'm just going to call that my apothem so we know what this is, okay? Where it's located. But if I have an isosceles triangle, that central angle is really called the vertex angle. What does this perpendicular segment do to that angle? That's right. It's going to bisect it. So this angle and this angle will be the same. That's actually critical for later. And we also use S for the side length. And I use curlies with my S because they look too much like my 5s. And we want to make sure we have that right. Also, don't forget that N equals the number of sides of a polygon. We're going to be using that again. We use this with the sum of the angles of a polygon, but we're going to use that again. Now, without going into too much detail, we did say that every one of these bigger isosceles triangles are congruent. So if I really wanted to find the area of that regular polygon, I could use, area equals base times height over 2, plug in my information here, and I'd actually have my base is going to be the side. My height would be the apothem, because I could use this triangle, and that'd be over 2. Now some people would go apothem times side over 2. It doesn't matter, okay? That's our area. But if I did the total area of the polygon, I'd multiply by the number of sides. So I'd go n times each triangle's area. Now, here's kind of one of those things. We're going to get a little sneaky here. Would you agree with me that perimeter is the number of sides, right? The number of sides times the side length itself. So I could actually rewrite this formula as apothem times perimeter over 2, because we're going to let P equals n times s, and I just multiplied those two together. Now, most of you don't really care how that's derived, but you do care about what formula you're going to expect. Sometimes you'll go 1/2 apothem times perimeter, use a capital P there, but you should know me well enough by now. I prefer area equals apothem times perimeter all over 2. And remember, your apothem comes from your center to the center of a side, and we're going to use perimeter as just the side times the length times the number of sides. We're going to use that to get there. Now, the best thing I know how to do this is just to apply this information, and the first thing we're going to do is going to practice finding angles in these, and then we're going to find the area. So let's flip to the next page.